Okay, we'll now discuss about the chapter called as Euclid's geometry, and we'll solve some problems based on Euclidean geometry. These are the problems from a worksheet, and I selected some, prepared a PowerPoint presentation of this. Let's just see this quickly. So the first problem is, let's see, if A, B and C are 3 points on a line and B lies between A and C, then prove that AB plus BC is equal to AC. Now this sounds very obvious, and this is the point about this chapter. What is extremely obvious for us was something that Euclid had to innovate and work around to create the logic for this. Because Euclid was not looking for basic ideas and logics which can be applied. He was looking for what is the origin and the basic background of geometry. So Euclid was, formulating the framework of the basic thing. This can be very easily understood because if we used our mobile phone, or let's say in a computer, and we are using basic softwares like PowerPoint I'm using, like we use Microsoft Word. These are the softwares that we install. Euclid was not creating or talking or innovating about a software. He was working on an operating system. The operating system like Windows. Once it is installed, then you can use other softwares. Without Windows, the softwares will fail. This is what the basic point of Euclid is. Alright, let's not spend much time on this now. We'll see that in the class. Now let's see, we'll just draw a diagram on this. A, B and C. Now B it might seem to be a midpoint. I don't mean that it is a midpoint. It is anywhere in between A and C, but on the same line. So A, B, C are the 3 points on the same line. Now what we have here is, please check that, it is given that the point B lies between A and C. AB is equal to distance from A to B. BC is equal to distance from B to C. Clearly AB plus BC would be the distance from A to B to B to C. So that is distance from A to C. So we can say that AB plus BC is equal to AC because it is based on the axiom 4, which says that the things which coincide with one another are equal to one another. So AB plus BC, it actually coincides with AC. And because they coincide, so the left hand side together, AB and BC together, is equal to AC. And this is what we have as the first question. Let's see the next one. Prove that equilateral triangle can be constructed on any given line segment. I'll just take a random line segment like this. This is AB. Now on this line segment that I have, with center at A, I'll draw a circle. Now do we need the entire circle? No, I only need up to this point because that is where I am going to construct the equilateral triangle. Not even consider by the show what the equilateral triangle will be like. So I don't need the entire circle, I get rid of this, only this arc I'll keep. So I keep this arc. Then I have the center at B and I get another arc. Very similar. Yeah. The two arcs intersect at this point that I call as point C. Now what I have here is, initially we had a center at A and the arc or the entire circle was drawn. So AB and AC are both radius with center at A and the entire circle can be drawn. So this is the radius and this is the radius as well. So I write AB is equal to AC because this is the radius of the same circle. Now when the center was at B, BA is equal to BC because that is also radius. So BA, I am writing AB is equal to BC. AB in BA same. So AB is equal to BC is the radius of the same circle. Now again we can use Euclid's axiom which is saying this AC is equal to AB and BC is equal to AB. So the things which are equal to the same thing are equal to one another. So AB is equal to BC because axiom 1 says that things which are equal to the same thing are equal to one another. That is how we get AB is equal to BC and we get AC is equal to BC. AB is equal to BC and AB is equal to AC is already established. So together all three are equal. So we write AB is equal to AC is equal to BC. AB is equal to AC is equal to AC is equal to BC. So if we cut these arcs and make a triangle out of it, we get an equilateral triangle. That is how we know that or with any base we can construct an equilateral triangle. Next, oh, this is really interesting. X minus 15 is equal to 10. We have to solve this. X minus 15 is equal to 10. X minus 15 is kept in the bracket plus 15. 10 plus 15. Anybody will say, why do this? Yeah, tell you why. Because this 15 to be transferred on this side, this is numerical adjustment, this is algebra. Euclid was not talking about algebra. For Euclid, this x minus 15 might have been, the area of one big plot or one big rectangle minus the area of something else. And then he is talking about the area of something else. Basically, we are talking about Euclid is initially basically talking about geometry. So we are trying to refrain from using the logics and understanding of algebra. So what I am saying is, if we cannot transfer this 15 on this side, but we can keep it very simple and we can say, if this is x minus 15, I will add 15 to it. Why add 15? Because it is minus 15 and plus 15 will get cancelled with each other. So I will be having x minus 15 plus 15 is equal to 10 plus 15. This is coming from again the same kind of axiom where the things which are equal and an equal number or equal is added to it. So when equal is added to equals, the wholes are equal. That is the axiom that we are using, that we are referring to. Axiom 2, if equals are added to equals, the wholes are equal. Because this is equal to this. And 15 and 15 both are equal added to them. So equals are added to equals, then the wholes are equal. Minus 15 plus 15 goes. X is equal to 10 plus 15 is 25. So you can solve this kind of equation using the Euclidean geometry. Next problem. Prove that two distinct lines cannot have more than one point in common. Alright, let's assume that more than one point can be common. This is called as indirect evidence. What are we doing here is, we are saying, okay, if we are to prove something, we'll assume the opposite, we'll assume the contrary. And from that contrary assumption, we'll walk down the path and we'll find out that it leads to contradiction. And then we trace it back and we say the contradiction happened because our assumption was wrong. So I'm making an assumption that more than one point can be common between the two distinct lines. So there are two distinct points A and B. I am not drawing a diagram because the diagram is impossible to draw. There are no 2 points which can be common to two lines. So how can I draw a diagram? So just stick to these two distinct points A and B are common between these two lines. There are two lines and in between these two lines 2 points are common. But an axiom 5.1 states that